Okay, so it is a very great pleasure for me to introduce our today's speaker, Professor Son. So Professor Son got his PhD from the Institute of Nuclear Physics in Moscow in 1995, and then he spent 2 years as a postdoc at the University of Washington and 2 more years at MIT, and started his first faculty appointment at Columbia in 1999. In 2002, he moved as a professor to the University of Washington, and since 2012, he was the 19th university professor at the University of Chicago. His research brought very significant recognition and numerous major awards, including the membership in the National Academy of Science and the National Academy of Art and Sciences. And now I think my job is to explain what the field of research of our today's speaker is. And honestly, it's extremely challenging task. And probably the best definition is that Professor Son is a theoretical physicist. Now, we, of course, know this thing that's often repeated, that in all time people were very broad, worked on everything, but now people are very narrow, everyone specializes, and then different sources would give us a different name of the last physicist who worked on everything. For example, sometimes it's told that Enrico Fermi was the last person who worked on everything, and sometimes it's told that Lev Landau was the last person who worked on everything, and then sometimes it's told that it was Feynman. But now, if you open the Wikipedia page for Professor Son, this Wikipedia article informs us that his main interests are quantum chromodynamics, string theory, and many body problems in condensed matter physics. And I can assure you that this is a very narrow description of his interests. For example, the class he is currently teaching doesn't fall under any of those rubrics. He is actually teaching cosmology. So we have someone who works on absolutely everything. And as another proof of this, you may remember that several years ago, he came to Brown as a guest of our high energy theory group. But today's talk is going to be on condensed matter physics. And today we will learn about a very original and very influential approach to the quantum Hall effect that our today's guest invented. Though, of course, this very original approach had a lot of influence not just on condensed matter physics, but also on high energy. So please welcome Professor Son at Brown.
Much, Dima, for the introduction. It is my great pleasure to give a colloquium at Brown. I'm going to tell you about something I have been working on for the last several, maybe 3-4 years. It's about fractional quantum Hall effect. I want to draw some connection to quantum field theory, namely describe to you how new insight on dualities in field theory has arisen from basically a problem of quantum Hall effect. And then at the end, I will describe to you how a new state of matter can arise from this new picture. So I would like to first recall the basic physics of the fractional quantum Hall effect as a non-perturbative problem, and then spend several transparencies on a traditional picture of the quantum Hall effect that I would call old composite fermion. Then explain how this old picture misses some deep symmetries of the problem, and an attempt to restore this symmetry leads us to a new understanding of the theory and the connection to field theoretical dualities. So let us first recall the classical Hall effect. The quantum Hall effect, of course, is a very one of the most surprising discovery in physics, but it has a classical counterpart that was discovered in the end of 19th century by Edwin Hall, who was at the time a graduate student. So he discovered that if one place a sample in a magnetic field and try to push a current through the sample, then there will be an electric voltage drop on the direction perpendicular to both the current and the magnetic field. And let me here introduce some notation that I will use later on. If one measures the current density as a function of the electric field, one can define the conductivity, which I call here sigma. But in the case of a sample in a magnetic field, there are actually two different conductivities. The longitudinal conductivities that I call sigma xx, and the other conductivity in the perpendicular direction that I will call sigma xy. So if I have the electric field along the y direction, there is a component of the current along the direction x. To explain the whole effect, one needs to just recall what we learned from classical electrodynamics. Charge moving in a combination of electric and magnetic field of force. And the force is proportional to the combination of E and B. E cross V, E plus V cross B is proportional to the Lorentz force. And if one average the force over many period of the rotation of the particle in the magnetic field, one would find, one would have to put the average of that quantity to 0, and from that one find the drift velocity V. So this drift velocity should be perpendicular to both the electric and magnetic fields, and knowing the drift velocity, one can compute the total current in the system. In 1980, a surprise was found when people, including Klaus von Klitzing and collaborator, discovered that measuring the Hall effect in very high magnetic fields, one finds not the classical expression, namely that the resistivity should be, the Hall resistivity is proportional to the magnetic field, but rather a stepwise dependence of the Hall resistivity on the magnetic field. And what is interesting about this step is that the values of the resistivity at the steps seems to be related to a combination of physical constant of nature, namely this rho xy is equal to h divided by e squared times 1 over n, where n is an integer. So that is called the integer quantum Hall effect. And the constant of proportionality here, this combination h divided by e squared, is now called the von Klitzing constant. It's one of the most precisely measured constant in nature. And it's surprising because this constant, the quantization of rho xy on each of these steps is 10 to the minus 9, which is very surprising in condensed matter physics, where the sample quality is by no means 10 to minus 9 purity. The integer quantum Hall effect can be partially explained by appealing to what Landau did in 1990. So as a young physicist, Landau, one of his first work was to quantize the motion of a charged particle in a magnetic field. So from classical to quantum correspondence, we know that if a particle moves in a periodic orbit, its energy level has to be quantized, and Landau solved the Schrödinger equation in a magnetic field. If the electron is confined to move in 2 dimensions, then the energy levels are all quantized. One can imagine a situation in which the chemical potential lies in between 2 Landau levels. Then the ground state of such a system will be a state in which all the energy below the chemical potentials are filled, and all the energy level above the chemical potentials are empty. So in this case, it's very easy to see that the system is very stable. There is an energy gap. In order to perturb the system, we need to spend energy to move one electron from here to an electron to the next Landau level. That explains qualitatively the stability of these quantum Hall plateaus, and appealing to some additional arguments, one can show that the whole conductivity would be equal to the number of field Landau level times the constant E square of H. 2 years after the discovery of the integer quantum Hall effect, Stormer and Gossard found another surprise, that is the existence of quantum Hall effect when only a fraction of a Landau levels are filled. So this is a slightly later plot. They found the appearance of the quantum Hall plateaus at filling fraction that is not an integer, but a fraction of an integer. To describe why this is very non-trivial, let us recall the picture of the Landau level again. So we know that when we have Landau levels, the degeneracy factor of each Landau level is proportional to the magnetic fields. The number of states at each Landau level is equal to the number of magnetic flux quanta going through the system. So if I increase the magnetic field, at some point there will not be enough electrons to fill even the lowest Landau level. So imagine a situation like this, we have only, here I imagine I have 6 orbitals on the lowest Landau level, but only 2 electrons. But one can imagine 6 million states in the lowest Landau level available to 2 million electrons. Then the problem becomes very non-trivial because there are so many ways to distribute the electrons among the unfilled orbitals. Let's define a quantity that we will call nu, which is the ratio of the number of particles over the number of magnetic flux quanta. For example, in this case, the number nu will be equal to 1/3, 2 electron over 6 states, so the filling factor equal 1/3. And the experimental finding of the fractional quantum Hall effect suggests to us that there are very stable quantum Hall state which has behaves in many ways in a very similar way as the integer quantum Hall effect, even when the filling factors are less than 1, for example, 1/3, 2/5, etc. So this problem is very non-trivial, and in order to describe the system, let's recall the existence of the energy scales in the problem. The quantization of the single electrons in a magnetic field give us one energy scale, which is the electron's cyclotron frequency, which if I multiply by h bar would give me the energy distance from one Landau level to the next Landau level. In the fractional quantum Hall case, there is another energy scale, which is the scale of the Coulomb interaction between the particles. This gives me a different energy scale, and in principle, this energy scale may not be related to the Landau energy scale at all, to the cyclotron energy at all. In fact, most of theoretical papers written on the subject of the fractional quantum Hall effect assume a limit of the lowest Landau level. That means we take the magnetic field to be so large that the distance to the next Landau level is very high. And theorists like this limit because it simplifies the problem. Instead of concentrating our attention to to all the Landau level. We can just focus on the single Landau level and try to understand how the interaction between the electron split energy level to multiple energy levels. But from the formulation of this limit, it is clear that perturbation theory shouldn't work. There is only one single energy scale in the problem, and there is no small parameter. In formulas, if we try to solve the quantum mechanical problem of a system of n particles moving in a magnetic field, one would have to try to diagonalize Hamiltonian, which consists of the kinetic energy and the potential energy. The kinetic energy is proportional to the cyclotron frequency, but as we have described, when all the electrons sit on the lowest Landau level, the kinetic energy is basically quenched to the same values for all the states. So from the practical purpose, for our practical purposes, the hierarchy between the energy scale has only one scale. There is only a Coulomb energy scale, but there is no kinetic energy. Kinetic energy can be set to 0. And that's a problem because when we do quantum mechanics, we like to use perturbation theory. We have H0, H interaction. But here, H interaction is the thing that gives rise to all the interesting physics. So, on the other hand, looking at the experimental data, we see some systematics of the fraction where the fractional quantum Hall effect arises. So, for example, one can see here a series of plateaus with filling factor that fit the pattern of n divided by 2n plus 1, where n runs in this graph from 1 to 2 to 3 to 4, but with higher sample, one can goes to n equal to 10. And there are also plateaus with filling factors n plus 1 divided by 2n plus 1, where n again run 2, this n plus 1 run 2, 3, 4, 5, etc. This systematics seems to suggest that there are some interesting physics behind just the fractional quantum Hall effect. More interestingly, if we take this n to infinity, these two series converges to nu equal to 1/2. And experiments seem to show that when the Landau level is half-filled, the state, the ground state, seems to be a Fermi liquid of something, some fermion. And these fermion quasi-particles at half-filling seem to move in a straight line. Although we are at very high magnetic fields, the electrons move in very curved circular orbit of very small radii. The quasi-particle in this state seems to be something that can move in a straight line. So this has to be an electrically neutral quasi-particle. And the question is, what is the nature of that quasi-particle, and how in a system where the fundamental particles are the fermions with charge 1, one would have a quasi-particle that carries no charge. So this puzzle was addressed, and for a long time, the standard theory of how this quasi-particle arises is a theory of composite fermion, which I will call an old picture of the composite fermion, as opposed to what I will later describe as a more modern view of the composite fermion. So the picture of the composite fermion that has been with us for many years is based on the idea of flux attachment. This idea came actually from the old theoretical fascination with anyons, which was popular with high-TC for some time as one of the candidates to explain high-TC superconductivity. But the idea is more general than that. If we have two fermions, we know that exchanging two fermions would give us a factor of -1 in the wave function. Let us now imagine that each of these fermions carries some number of flux quanta. And in this graph, I consider a particular case when each fermion is attached with two flux quanta. You imagine a composite object in which a particle is a solenoid through which there are a number of magnetic flux quanta. Then doing the same adiabatic exchange of two particles, we get an additional factor from the Aronoff bomb phase when a charge moves in a magnetic field. And that phase can be computed to be exponents of 2 times I pi, where 2 is nothing but just the number of flux quanta that we attach to each particle. E to the 2I pi is equal to 1, so the factor is -1. And so the statistics of this particle would still be fermions. The idea is to imagine that one can represent an electron at another particle, traditionally called the composite fermion, with 2 additional flux quanta of some additional gauge field attached to it. This seems to be quite a wild idea, but it gives rise to a very non-trivial explanation of the behavior of the quantum Hall effect at half filling. Because if we have fractional quantum Hall effect at nu equal 1/2, that means that with each electrons we have in average 2 magnetic flux quanta. So instead of plotting a homogeneous magnetic field, I draw here just a number of arrows, and each arrows correspond to 1 magnetic flux quantum. Now, if we can do a procedure of replacing an electron with a composite fermion with 2 flux attached to it, and then imagine that we can smear out the magnetic field uniformly by doing some sort of a mean field approximation, then the average magnetic field would end up to 0. The magnetic field, the artificial magnetic field that we have introduced through the flux attachment procedure completely cancel out the external magnetic field. The composite fermions then live in an average 0 magnetic field, and that means they can form a Fermi surface, like just free fermions in free space. So that's the idea of composite fermion and why the nu equal 1/2 state is a Fermi liquid. It's a Fermi liquid of some composite, some different type of particles. And the same procedure can be done for other filling factors. And I will not go through the arithmetics here, but the idea is that if I introduce the composite object that carries additional magnetic fluxes, then the magnetic field will be reduced. When the average magnetic field is reduced, that means the filling factor got enhanced. And in the case of the electrons with filling factor n divided by 2n plus 1, we can compute and see that these new particles, the composite fermion, would be in a state with n filling n Landau levels, because the magnetic field becomes so small that we need to fill n Landau levels to accommodate all the fermions. Similarly, when nu equal n plus 1 divided by 2n plus 1, the composite fermion would fill n plus 1 Landau levels. And these are integers, and we know that for integer filling factor, we have a gap state. We need to spend energy to excite that state, and so that would explain the emergence. I'm sorry, somehow I turn it off, turn on again. That would explain the fact why these states are special. They correspond to integer quantum Hall effects of the composite fermion. So they are gap states. So that is the end of the old story that started with James and some other people. It was with us for a long time, but there seems to be one mystery, one missing feature that is, we don't know how to fit that in this story. And this is a symmetry called the particle Hall symmetry. Imagine that we have a state that lives on 1 Landau level. That is, we concentrate our attention on a favorite limit of theorists, where all the Landau levels, except the lowest one, are kept, are thrown away. So we keep only one Landau level. That means all the states can be imagined as a linear combination of state with where each orbitals have occupation number either 0 or 1. So this is one typical of such a state. We filled these states and then left the other for orbital empty. Particle-hole conjugation is an operation where we flip the occupation number. We just change all the empty orbital to filled and filled to empty orbital. And actually that procedure can be defined mathematically in a way that does not depend on the basis of the that we choose for this orbital. In order to do that, we have to define that as an anti-unitary transformation, etc. I will not go into details. But this is a good symmetry of the Hamiltonian where we project it to the lowest Landau level. If all physics happen only on the lowest Landau level, and if the interaction between particles are two-body interaction like Coulomb interaction, one can show mathematically rigorously that this is a symmetry of the system. Moreover, this symmetry is a symmetry that maps filling factor nu to 1 minus nu, obviously. And so if nu is equal 1/2, that means it mapped through particle-hole symmetry is mapped to nu equal 1/2, because the number of particles and the number of holes is the same when we map particle into hole. So a half-empty Landau level is the same as a half-full Landau level, even at the level of the Hamiltonian. But if we try to understand how this symmetry manifests itself at the level of the composite fermion, then we hit a very difficult problem. We know from experiments that quasi-particles in the lowest Landau level are some sort of a neutral quasi-particle that form a Fermi surface. So the ground state is just a Fermi surface, a field Fermi sphere in momentum space. Particle-hole symmetry seems to map particle to hole. So if we naively replace particle with hole, we would get a state in which all the states inside a sphere, a Fermi sphere, are empty, and the state outside the sphere are filled. And that is, of course, a nonsense. There is nothing like this in any textbook in statistical mechanics. Moreover, this asymmetry of the usual composite fermion picture reflects itself in our understanding of the basic quantum Hall state like nu equal 1/3 and nu equal 2/3. The composite fermion interpretation of this state assigns such a state with n equal to 1 to one field Landau level of composite fermion. And this state with twice as many electrons as that state would be a state with two field Landau levels. And that discrepancy persists with any other pairs of states that should map from one to each other under particle-hole symmetry, but the composite fermion picture of this state are not. So we have a very good theory, the composite fermion theory, that seems to explain a lot of facts about quantum Hall effect, but it misses one fundamental symmetry. So coming from as someone entering the field, I was struck by the fact that that symmetry, that missing symmetry, was that problem with composite fermion theory was known for many years, but somehow people seem to have made peace with it. Lacking in high energy physics, symmetry plays a very big role. I think in all physics, symmetry plays a very big role. And if we are missing some symmetry, that means that we don't completely understand how the low energy effective theory should look like. So it has been known since 1997, but this problem, at least. But only recently a solution has appeared. And the solution is based on a different picture of the composite fermion. The composite fermion, we still think that near half filling, the low energy effective quasi-particle is a fermion. But that fermion is a Dirac fermion. It has a Fermi surface because there is still a finite density of this composite fermion. But the Fermi surface of this composite fermion is additionally characterized by a Berry phase that one gets by dragging a composite fermion around that Fermi surface. So let me explain in some picture how that works. Of course, graphene is one example where the Dirac fermion appears in condensed matter physics. If we take carbon atoms and arrange them in a two-dimensional lattice, hexagonal lattice, then the band structure of the low energy electrons would have two so-called Dirac points in the Brillouin zone, and around this Dirac point, the Hamiltonian is effectively the Dirac Hamiltonian, H equal to V times sigma dot P. It is different from the Dirac Hamiltonian familiar to high energy physicists by the lack of another sigma z pz term. We are here in two dimensions, so this is a Dirac Hamiltonian in two dimensions. The Dirac fermion here has only two components, and they correspond to two different energy bands in the problem. The valence band in the conduction band, and the two band near this point touches, and the energy near this touching point is linear in momentum, in the deviation of momentum from the Dirac point. So if one now try to understand the Fermi surface gas of this Fermi gas of these fermions, then one would have a Fermi, one would form a Fermi surface of these Dirac fermions. One can define a Berry phase that knows only about the properties of the fermion near the Fermi surface and still keep the information about the Diracness of the fermions. And that characteristics is called the Berry phase. So in order to define the Berry phase, one would find the eigenvalues of the Hamiltonians that I have written on the previous transparency. So for positive energy eigenvalues, I define this vector to be UP. It is a two-column vector, and using this UP, one can define the connection, which is a connection in momentum space. But that connection in momentum space, H of P, has the properties that the integral of that connection around any curves that surround the origin is equal to pi. So the fact that this Berry phase is equal to pi is the characteristics of the Dirac particles. So the theory of the idea of the composite fermion, Dirac composite fermion, is that these composite fermions exist, but they have a Berry phase of pi around the Fermi surface. Let me show you two arguments showing that the composite fermion in the fractional quantum Hall effect has to be a Dirac particle. The first argument is actually not really an argument, it's a hint, but it's based on the naive attempt to reconcile the old composite fermion representation of the two filling factors in the quantum Hall effect. So we have mentioned that there is two series of quantum Hall plateaus with filling factor n divided by 2n plus 1 and n plus 1 divided by 2n plus 1. And they correspond in the usual composite fermion picture nu, the filling factor equal to n, and filling factor of the composite fermion equal to n plus 1. So the mismatch between these two numbers is the things that breaks the particle-Hall symmetry of the old composite fermion representation. In order to reconcile these two numbers, let us try to replace them by the average, that is n plus 1/2. So let us try to understand if there is a solution to this discrepancy in which the filling factor of the composite fermion is actually n plus 1/2. Now, this is not an integer, so the old solution to the old explanation of the fractional quantum Hall effect is based on the fact that the composite fermion fills an integer number of Landau level. Here we are trying to posit that the composite fermion fills a half integer number of the quantum of the Landau level. So it seems that we are breaking, in order to restore the particle-Hall symmetry, we break a very nice aspect of the quantum Hall, of the existence of the quantum Hall of the composite fermions. But we know that a Dirac fermion actually forms a quantum Hall state with a half field, with a half integer filling factor. It's very easy to explain on this diagram. Imagine that we have a massless Dirac fermion in a magnetic field. We can repeat the calculation of Landau and find all the energy level of a relativistic particle in a magnetic field. And we see that there is one very special Landau level that remains at 0 energy all the time when we turn on the magnetic field. That was the Dirac sea. That was a field Dirac sea, and these states are still have negative energy and still filled. This state is above the Dirac sea, and they are unfilled. But there is one special Landau level, which we have, all the orbitals have 0 energy, and we have to decide which one to assign occupation number 1, which one occupation number 0. And this cannot be done without taking into account the interaction between the particles. But we expect that if we have taken that into account, that state with 0 chemical potential has to have effectively a half-filled Landau level. And so that a half discrepancy explains why when people measure integer quantum Hall effect in graphene, which is one of the first experiments done when after graphene was created, observe that the plateaus, the integer quantum Hall plateau in graphene fit with the contribution from each Dirac fermion to be a half integer of the quantum. So Dirac fermion naturally give you an integer quantum Hall effect with a half integer filling factor because of the fact that the 0 Landau level is both particle and Hall at the same time. The second argument is a little bit more involved, and I will only sketch the idea of the argument. One can show that this particle-Hall conjugation as an operator has a square that can be either +1 and -1. Theta is an anti-unitary operator, and its square is +1 or -1 depending on how many, on whether the number of, whether it's +1 and or -1 depends on the number of orbitals on the lowest Landau level. In the case when the number of orbitals is an even number, that theta square is either +1 or -1 depending on whether that number is divisible by 4, or when it divides by 4, give you its division. Give you mod 2. And that statement can be proven rigorously by just looking at the definition of the particle-Hall conjugation. It doesn't depend on the Hamiltonian at all. It just depends on the Hilbert space of state in the lowest Landau level. And now this means that if we have a low energy description of the quasi-particle, it must know about these properties of this operator theta. In fact, it can be matched with Dirac composite fermion very naturally, if we decide that the number of composite fermion is equal to the number of orbitals divided by 2, and then this theta square is just equal to -1 to the power of the number of composite fermion. So that operator theta square becomes the operator theta square becomes just the parity of the number of the composite fermion. That's an operator that can be defined in the theory of the composite fermion. So this is the second argument that one can give to show that from a purely logical reasoning, one can deduce the Diracness of the composite fermion. Now we think that this explanation of the quantum Hall effect is a manifestation of a deep duality within quantum field theory in 2+1 dimension. Namely, that a theory of a Dirac fermion in 2+1 dimension, so here is my Dirac Lagrangian psi is a 2-component Dirac fermion coupled to an external field A mu, is the same as the theory of QED in 2+1 dimension. So here I write down a simplified version of that theory. In fact, if one tries to be rigorous, the Lagrangian is a little bit more cumbersome. But in the idea here is that there are some representation of free fermions in terms of fermion interacting with a gauge field. And this theory is strongly coupled. The coupling constant runs to infinity in the infrared as a gauge theory, as in any gauge theory in 2+1 dimension. And the claim is that in a strong coupling, this theory reduces to a Dirac fermions in a non-interacting Dirac fermion. So this is a fermionic version of the old particle vortex duality. Fermion here can be understood as a vortex with respect to the other side of the duality, and vice versa. And this is now, we think that this is one example of a very large class of dualities, of a whole web of dualities in 2+1 dimensional field theory. It is amazing that quantum Hall effect, which is something that can be probed experimentally, was actually the first thing that suggested for us an example of a new duality in 2+1 dimensional field theory. The Dirac composite fermion has several predictions, some of which are more non-trivial than the other. So let me go through some of these predictions. One set of predictions is on transport, and these are, strictly speaking, consequences of particle-Hall symmetries rather than of the Dirac composite fermion that realizes this particle-Hall symmetry. But these predictions are satisfied in any theory with particle-Hall symmetry, in particular the Dirac composite fermion theory. Namely, at half filling, the whole conductivity has to be equal to E squared over 2h exactly, and one longitudinal thermoelectric constant, that is the current induced by a gradient of the temperature, has to be equal to 0. As far as I know, this prediction has never been tested in experiment. It also assumes certain, it also makes certain assumptions on the nature of the impurities that might or might not be well satisfied in the real experimental setup. Another prediction which was verified numerically is the absence of Friedel oscillation in a correlation function of certain operators. Namely, if one has two operators, we have an operator that is particle-Hall symmetric, then in the correlation function of that operator, one should not see any Friedel oscillation. And that has been seen experimentally. Numerically in numerical experiment. But one consequence or one suggestion of the Dirac composite fermion theory that I would like to talk about is the existence of a new gap phase that is called the pH fermion or particle hole fermion state. Let us imagine that the composite fermion at half fielding has some, they interact with each other in a way that we cannot compute theoretically in a reliable way, but let us imagine that the interaction between this fermion is such that they can form Cooper pairs. We know that Cooper pairs can be formed in rather generic, with rather generic interaction. We just need interaction in BCS channel to be attractive. But once it is attractive, Cooper pairs would form and a new state of matter would be formed. A superconducting state in the case of metals. In the case of pairing of the composite fermion, that would lead us to a gap phase, a quantum hole plateau. So the simplest pairing that we can form from Dirac fermion does not break particle hole symmetry. It is a pairing which is in some sense in the S-wave channel. Even these are fermion, it can form a pairing in the S-wave channel because these are the Dirac fermion with the Lorentz index. So we can form an anti-symmetric structure from this fermion without using any derivatives in space. It turns out that this state actually is a new state that has not been considered before. It's a new gap state that has non-abelian quasi-particles, similar to some other state that has been proposed. But this is a state which, if the microscopic Lagrangian, microscopic Hamiltonian is particle hole symmetric, would preserve that symmetry. So we call that state a pH fermion state. And it is now considered as a candidate for a quantum hole plateau at nu equal 5 half. Nu equal 5 half is probably is one of the rare example of a quantum hole state where the denominator is an even number. Most of the quantum hole plateaus happens when the denominator is an odd number, like 1/3, 2/3, or 2/5. But in the case of 5 half, which was known for a very long time, we have a plateau at filling factor that has the denominator that is even. And it was realized very early on that the nature of this state is very different from the nature of the usual quantum hole plateau, say at nu equal 1/3. The nature of that state now is still not known. The leading candidates for this state are the so-called fermion or anti-fermion state. That are the state that was proposed very early in the just a few years after their experimental discovery in the case of the fermion state, or about 10 years ago in the case of the anti-fermion state. But each of these states seems to contradict certain measurements. So no state would explain the whole set of all the measurements that are done in experiments. So Dima was actually the first who noticed that the pH fermion state has the properties that fit almost all, that makes this contradiction between different measurements go away. There are two different measurements that can be, one tell you that the state is likely a fermion state, another measurement, one measurement on the existence of the so-called counter, the upstream mode will tell you that the state is an anti-fermion state, another measurement of an exponent in tunneling experiment give you a fermion state, but the pH fermion state seems to fit both experiments at the same time. Right now, the situation is not very clear. The numerical simulation seems to disfavor the pH Pfaffian state. But these numerical simulations are done in a very ideal situation. In particular, they do not take into account impurities, and they take into account the mixing between different Landau levels in a rather schematic way. And so right now we actually don't know what is the state that is favored for the nu equal 5/2 state. There is a very interesting recent experiment done in Heilbrun's group when they measure the hole conductivity, but it's not the usual hole conductivity, but it is the thermal hole conductivity when we impose the gradient of temperature from one end of the sample to the other end and measure the heat currents flowing across the sample in the perpendicular direction. Different quantum hole state, different topological structure of the state predicts different values for this thermal hole coefficient. So normalized to a number that is called kappa 0, the Pfaffian would correspond to the conductivity, the thermal hole conductivity 5/2, anti-Pfaffian correspond to 1.5. The measurements surprisingly seems to suggest that the state is a pH Pfaffian state, although it was a surprise, at least for theorists, because we have the biased based on numerical simulation that the state has to be Pfaffian or anti-Pfaffian state. For most of the theorists, it was a surprise, maybe not to Jima, but to most of us, it was a big surprise that the state seems to be the nu equal 5/2 state might be the pH Pfaffian state. So let me conclude. Dirac composite fermion is an emergent quasi-particle of the fractional quantum Hall effect. Now, I would like to emphasize here the word emergent. This is the particles that, by its properties, are very different from the electron. They are electrically neutral, while the electrons are electrically charged. The number of these composite fermions are not the same as the number of electrons. They are not the same as the number of holes. But this number of the Dirac composite fermion is just some number related to the magnetic fields that you push through the system. Interestingly, it is an experimentally accessible system realizing a non-trivial particle vortex duality, which is one of the dualities central to new activities in high-energy physics, investigating non-trivial relationship between non-trivial equivalence between theories which have very different Lagrangians. Pairings of Dirac composite fermion leads to quantum Hall states. Leads to different quantum Hall states depending on which channel the pairing happens. If we pair the fermion in the simplest channel, we get the so-called pH Pfaffian state. But if the pairing happens with angular momentum +2 or -2, we would get the Pfaffian or an anti-Pfaffian state. And low energy effective theory cannot tell us which pairing happened, whether pairing happened or if it happens in which channel that happened. What we know is that the pH Pfaffian state is the state where the pairing wave function has a simplest structure. But simplest doesn't mean that most energetically favored. But surprisingly, the observed nu equal 5/2 state may be the pH Pfaffian state if the results of the newer experiments are confirmed. Thank you very much.
Questions? Yes.
So you mentioned your theory is based on this particle Hall symmetry, and then you emphasize that parallel with particle vortex duality, Is that just an analogy or more than that?
What particle hole to, okay, so maybe, no, this one would not be, I don't have the transparency, but the particle, so the particle hole symmetry in one side of the duality map to symmetry that looks like time reversal on the other side. So a particle hole in relativistic context is a CT symmetry, a combination of C and T, and on the other side that CT symmetry realizes as if it is a time reversal. But yeah, the name particle vortex refer to the fact that the current, fermionic current on one side mapped to field strand on the other side. Yeah.
Can you elaborate on this particle vortex duality? I remember in the context of a Josephson junction array, Matthew Fisher made the point of this superconducting to insulating transition in that system.
Yeah.
It also has this particle vortex duality.
Yeah, so it is exactly, it is very similar to that duality. There, the duality is between, so the map is between a theory in which the particles are the, say, the Cooper pair, the boson. That boson in another formulation would be a vortex, and vortex in that formulation is a boson in this theory. Here, an electron is mapped to, it's like a fermionic vortex in another theory, and the fermion here would be a fermionic vortex in the other theory. So what is not non-trivial here is the fermionic nature of both the particle and the vortex on the two sides. And a little bit non-trivial distinction between the two particle vortex duality is that in the bosonic particle vortex duality, the boson has to be near a Wilson-Fisher fixed point, and in the fermionic case, it can be just a free fermion.
So to realize fractional quantum Hall effect, you need a very strong magnetic field, sometimes tens of Teslas. And that may limit its application if it can be useful. So the question I have is it possible you can put a 2D electronic system in close proximity with a ferromagnetic insulator, so to take advantage of the exchange field to get the same kind of physics?
I think a lot of people are now interested in so-called Chern bands where you engineer, instead of, so in order to have a fractional quantum Hall effect, one needs to have a very flat band so that the Coulomb energy is very large compared to the width of the band. And so there are a lot of activities on Chern band and how to realize fractional Chern insulators. Probably some of this intuition about the composite fermion should be applicable there. I don't know any, like, do you know any experimental? I don't know any experimentally realized Chern band at this moment. It seems to be promising.
So one thing that one can realize with just, in free fermionic systems are things like singlet states that can create entangled states. Does this duality accommodate entangled states?
It should, but I haven't studied any question related to entanglement. In fact, it may be non-trivial because on one side of the duality, we have a gauge theory and it's subtle. Another thing, I think why it is subtle, because the mapping between the degrees of freedom from one side to another side must be non-local. So the fermion there is no explicit mapping at this moment, so we don't know how they would look like. But with the non-local mapping, it's probably non-local, and how entanglement change. Does it change when we go from one side to another is something I don't understand.
So you mentioned that you came to all this philosophy and dualities working on as a quantum Hall effect problem, but there are many more dualities than just the one that emerges in the particular quantum Hall problem of the filling factor 1/2. So I wonder, do you think that those dualities can be helpful to understand other materials,
Other materials.
other than quantum Hall systems, other classes
Yes.
of condensed matter systems?
Yeah, in fact, it may be, but I know I only know that people worked on an example of the duality where the system is gauge theory coupled to two Dirac fermions. The claim is that it may be related to a spin liquid state, and this theory also has very nice self-dual structure, and it has emergent low energy enhanced symmetry. So in spin liquid there might be some application of the new dualities.
Okay, so I think it's time for us to thank our speaker again.